Let's talk about the work done in different thermodynamical processes. So we are very well about this formula that the work done is equal to integration of P dV from volume V1 to V2. Okay, and some basic things before we go ahead with respect to this is the following. Suppose if the gas expands, then V1, suppose V initial, and it expands to V final. That means V final is definitely greater than V initial. The volume of the gas increases. In this case, we say that the work is done by the gas, and this work done we consider positive. On the other hand, during the contraction of the gas contracts, volume decreases. That means Vi to Vf, and Vf is smaller than Vi. In this case, work is done on the gas, and we consider this work done as negative. All right. Now let's move ahead. Suppose we take the first process as isobaric process. Now in isobaric process, the pressure is constant. We are very well aware about this fact. So now in case of the isobaric process, the work done, we are going to use the same equation. This can be used for all processes. Correct? Now one more thing, that since we are talking about the gas, and the gas is an ideal gas, so we can use PV is equal to mu RT in any of the cases, because we are supposed to investigate the work done by the gas, and the gas itself is ideal gas. So we can use this equation in any given kind of thermodynamical process, whether it may be isobaric or isochoric or isothermal or whatever it may be. We are going to use this anywhere, right? So over here we don't require to use this equation because P is constant, so it is going to come out of the integration part, dV from V1 to V2. Now this is equal to P. Now integration of dV is V, then from volume V1 to V2. So that means this is equal to P upper limit, that is V2 minus V1. We also write this as P delta V. Now whether depending upon volume V2 is greater than V1 or V1 is greater than V2, you will get this as positive or negative. Okay, so this was the formula for the work done in an isobaric process. Let's talk about isochoric process. Now in isochoric process, volume is constant. Now since the volume is constant, let's write this formula again, P dV from V1 to V2. If I say volume is constant, that means change in volume, whether it may be large change in volume or small change in volume, that is 0. Since volume is constant, there is no change in the volume, so the final and initial volume are the same, so change in volume is 0. So you directly substitute dV as 0, so the work done itself is 0. This is the expression for work done in an isochoric process. Now let's talk about the work done in isothermal process. So now in the isothermal process, the temperature is constant. Let's use W is equal to integration of P dV from V1 to V2. Now what we are going to do is the following. We are going to say that PV is equal to mu RT. Now from here we are going to substitute the value of P as mu RT by V. So this value of P I am going to substitute here. So the work done is equal to integration from volume V1 to V2, that is equal to mu RT by V times dV. Now if you look carefully, mu, the number of moles of the gas, is constant. When we talk about the work done on the gas or work done by the gas, we don't usually change the volume of the gas. So mu constant, R constant, T is constant due to the fact that it's an isothermal process. So these three will come out. So that means work done is equal to mu RT integration of 1 by v dv from v1 to v2. Now in maths you already know that integration of 1 by x dx is natural log ln, that means to the base e, times x, like this, ln x, that is log to the base e, not to the base 10, right? So in the same way, now since mu r and t are constants, they are going to come out, so mu r t, and integration of 1 by v is natural log or log to the base e times v from v1 to v2. Now work done, that is equal to mu r t, that is equal to ln v2 minus ln v1. Please note, when we substitute the limit, there is no constant. Otherwise, if you don't put the limits, you will have to add a constant. But if there are limits like x1 to x2, that means this c is not required. Okay. So here, since we are putting the limits, plus constant is not required. Now we do know the fact that log a minus log b is equal to log a upon b, like this. So this is the expression for the work done. Please note that if v2, that is the final volume, is greater than v1, because we say that the volume of the gas was v1, then it expanded to v2 or contracted to v2. So this is initial volume and this is final volume. If v2 is greater than v1, that means this is a pure case of expansion. And in this case, this will be bigger than this whole number v2 by v1 is greater than 1 and log will be positive, so the work done will be positive. But if v1 is greater than v2, that means this is a case of contraction. In case of contraction, this will be less than this, the number will be less than 1, and in that case the log is negative. So that means the work done would be negative. So now let's derive the expression for work done by the gas in an adiabatic process. So let's assume an ideal gas at pressure P1, volume V1 and temperature T1. Now let's expand this gas adiabatically to a new state, and let's assume the pressure to be P2, volume to be V2 and temperature T2. Of course, when volume expands, so V2 is greater than V1. Alright, now we can use this PV is equal to mu RT anywhere, because we are dealing with the ideal gas. So this gas is basically ideal in nature, so we can use this anywhere. Alright, even during the adiabatic process. But we have a special equation for an adiabatic process, that is PV raised to gamma is equal to some constant. Let me assume this as K. I can also write this as P1 V1 raised to gamma is equal to P2 V2 raised to gamma. So when this volume increases, this pressure has to go down. So when volume expands, this pressure decreases. But we are interested in what happens to the temperature as well. Alright. So when work is done, or when expansion takes place, work is done by the gas. So basically this work is positive. So during this process, which temperature is greater, that is what our intention is to find out, and let's derive the work done expression as well. So work done is equal to integration of P dV from volume V1 to V2. So what am I going to do is, I am just going to substitute the value of this P as, so the work done, that is equal to integration from V1 to V2. This pressure can be written as K upon V raised to gamma times dV, because this V raised to gamma goes down. So now this K is going to come out. So integration from V1 to V2, that is 1 by, or we can also write down V raised to minus gamma dV. Now we do know the fact that integration of x raised to n dx is equal to x raised to n plus 1 upon n plus 1, like this. So over here also what is going to happen is V raised to minus gamma plus 1 upon minus gamma plus 1. Now lower limit, upper limit. So what we are going to do now in the next step is, we are going to substitute, this is V1 to V2, upper limit over here, K, then this V2 is going to be plugged here instead of this V. So V2 minus gamma plus 1 minus lower limit, I am going to plug this over here, that is V1 minus gamma plus 1. Now this minus gamma plus 1 is constant, so I am going to pull it out of the bracket like this. Okay, so this is being pulled outside, upper limit minus lower limit. Okay, so this is again K times minus gamma plus 1. Now this can be, this can be written as V2 raised to minus gamma times V2 minus V1 raised to minus gamma times V1. I hope you have understood this well, because anyhow when the bases are same, the powers get added up. Okay, now I'm going to push this k inside, so I'm going to remove this k from here, and k is going to get multiplied over here. You will understand why did I do that. So W is equal to, now what do we have here? 1 upon minus gamma plus 1. Now instead this is P1 V1 raised to gamma, P2 V2 raised to gamma is k, right, because that is constant. So over here this k I'm going to plug in this value, so P2 V2 raised to gamma, and then followed by this V2 raised to minus gamma times V2 minus this k I'm going to plug in this value, P1 V1 raised to gamma times V1 raised to minus gamma times V1. Now these two simply gets cancelled, so work done is equal to 1 upon minus gamma plus 1 times P2 V2 minus P1 V1. Now we can't leave this expression like that, because see, this gamma number is greater than 1. So we will have to flip the sign. So what am I going to do is, I'm going to simply write this as 1, this is 1 minus gamma, so I'm going to write down gamma minus 1. So that means I am multiplying up and down by minus 1. So here also the sign gets changed, P1 V1 minus P2 V2. What did I do? Minus 1 multiplied up, minus 1 multiplied down. So that means this P1 V1 can be written as, since we are dealing with the ideal gas, now this looks fine, because see, the gamma is number which is greater than 1, so this looks fine, this becomes positive. Otherwise you will have to deal with this negative part always. Alright, so this can be written as P1 V1 is equal to mu R T1 minus P2 V2 is mu R T2. Now mu R is going to get common, let's pull this out as a common part. So mu R divided by gamma minus 1 T1 minus T2, this is the expression of the work done. Now let's analyze this one. Since we had considered a case of expansion, so work done is positive, because in case of expansion work is always done by the gas, right? So this is positive. Now this part is positive because mu and R are positive. Gamma minus 1 is going to be a positive number. This means this has to be positive in order to get this number positive. And this can only happen when T1 is greater than T2. That means initial temperature was larger and the final temperature was smaller. That means the gas cools down. So when the work is done by the gas in an adiabatic process, the gas cools down and the temperature of the gas decreases. Because see, once again I am saying, when this is positive, this part is already positive. So this has to be positive, for that T1 has to be greater than T2. Just the opposite, when the work is done on the gas, that means when the work is negative, at that time the gas compresses and the initial temperature is smaller than the final temperature. That means the gas heats up during adiabatic compression. So these are the things that you must understand.